All right, let's get you ready to absolutely crush your chemistry exam. We're going to focus on the core calculation questions that really make or break your grade. So let's just dive right in. You want to score full marks in stoichiometry, right? Of course you do. Well, these topics right here, they're the ones that decide your final result. So our mission today is simple. We're going to master them, and we are going to do it fast. First up, empirical and molecular formulas. This is a super important skill, especially when you're analyzing something you've made in the lab. It's all about going from the simplest possible ratio of atoms to, the actual real-life formula of a molecule. Okay, let's make this crystal clear. The empirical formula, that's the one on the left, is just the most basic stripped-down ratio. Think CH2. But the molecular formula, over on the right, that's what the molecule actually is, like C2H4. So one is the simplest idea, the other is the real deal. So how do you get from one to the other? It's a really simple two-step trick. First, you find this little multiplier, we'll call it N, by dividing the molecular mass by the empirical formula mass. Then you just multiply the entire empirical formula by that number N. So look at the example. For CH2, the empirical mass is 14. If the real molecular mass is 28, then N is just 28 divided by 14, which is 2. Boom, the molecular formula is C2H4. Easy, right? All right, your turn. Quick check. You've got an empirical formula of NO2 and a molar mass of 92. What's the molecular formula? Go ahead, pause here and work it out. And we're back. Did you get it? The answer is N2O4. The empirical formula mass for NO2 is 46. You just take 92 divided by 46, and that gives you your N value of 2. You multiply NO2 by 2, and you get N2O4. Let's keep moving. Next up, a concept that trips up a lot of people, the limiting reactant. The easiest way to think about this is like it's the one ingredient in your chemical recipe that you run out of first, and it brings the whole reaction to a screeching halt. The formal definition is exactly that. It's the substance that gets completely used up first in a reaction. Once it's gone, the reaction is done. Finito. It doesn't matter how much of the other stuff you have left over. Okay, let's solve one. Look at the reaction to make water. The recipe, the ratio, is 2 moles of hydrogen for every 1 mole of oxygen. Now look what we have, 4 moles of hydrogen and 1 mole of oxygen. To use up that 1 mole of oxygen, we only need 2 moles of hydrogen, but hey, we've got 4. That means our hydrogen is in excess, and the oxygen is going to run out first, so O2 is our limiting reagent. Okay, another quick check for you. Same reaction, but this time you have 2 moles of hydrogen and 2 moles of oxygen. Which one is the limiting reagent? Go on, figure it out. The answer is hydrogen, H2. But why? Well, the ratio is still 2 to 1. To react with all 2 moles of the oxygen you have, you would need 4 moles of hydrogen, but you've only got 2. So that hydrogen is going to be gone long before the oxygen is, and that's what makes H2 the limiting reagent. All right, on to our third topic, percentage yield. This one just tells us how efficient our reaction was. In other words, did you actually get as much product in your beaker as the math said you were supposed to? The calculation here is super straightforward. The formula is your actual yield, that's what you actually measured in the lab, divided by the theoretical yield, that's what you should have made on paper, and then times 100. So if you were supposed to get 10 grams, but you only got 8, your yield is 80%. Now, a very closely related idea is percentage purity. This isn't about the reaction's efficiency, but about the quality of your starting material. You know, how much of that stuff you're using is actually the chemical you want, and how much is, well, junk. And again, the formula is simple. It's just the mass of the pure stuff divided by the total mass of the whole sample times 100. So if you've got a 20-gram chunk of something, but only 15 grams of it is the actual pure chemical you need, your sample is 75% pure. Our final key topic is percentage composition by mass. This just tells us what percentage of a compound's total mass comes from each individual element that's inside it. The formula is again pretty simple. You take the mass of the element you care about, divide it by the total molar mass of the whole compound, and then multiply by 100. Let's use the classic example, water, H2O. The total mass is about 18. The mass of that single oxygen atom is 16. So 16 divided by 18 times 100 tells us that water is about 88.9% oxygen by mass. Okay, time for a final challenge to bring it all home. I want you to find the percentage of carbon by mass in carbon dioxide, CO2. Go ahead, pause this explainer and solve it. You got this. And the solution is 27.27%.
The molar mass of CO2 is 44, and the mass of that carbon atom inside it is 12. You just divide 12 by 44 and multiply by 100. It really is that simple.
So let's do a super fast rapid-fire recap. Empirical formula, simplest ratio. Limiting reaction, reaction stopper. Percentage yield, reaction efficiency. Percentage purity, how pure your sample is. And percentage composition, that's the element's contribution by mass. Got it? Look, you master these 5 concepts and you are absolutely 100% exam ready. The next step is just putting them all together in those big stoichiometry problems. You have the tools now, so go practice.